All right, so I wanted to talk a little bit about just the introduction to 3.1 so you could get going on your assignment for today. So yesterday after your test, what you should have done is the tangent line exploration, so the introduction to tangent line. And this is really the first time that we will get into calculus. So the idea of the derivative, which is what we're going to study next, is that we are trying to find the slope of a tangent line. And if you would go, I don't have the capability to show on my document camera, I don't believe. But if you would go and Google secant line animation or tangent line animation, essentially what a tangent line is if I had some function f of x, okay? The tangent line is a line that intersects at one point. So if I wanted the tangent line down here, okay, it touches at one point. And that tangent line essentially, if I wanted to move that point around, what it would do is it would change. So the slope of it would change. If the tangent line was up here, it would go like that, levels off, maybe goes down a little bit, and then up a little bit. So the issue that we run across is that a secant line is going to be a line that is connecting 2 points. So let's say I had this point and this point, okay? So this is a secant line. It connects the 2 points. The slope of the secant line is an approximate of the slope of the tangent line. The slope of the tangent line is at 1 point, and so here we come across a problem. Okay, normally the formula for slope for two ordered pairs is y2 minus y1 over x2 minus x1. And so what happens then is you subtract the y's and see how I have 2 points to do that. Well, if I had a 1 point, what would happen is I would have the same point here, so I'd be dividing by 0. Okay, this ties into limits because what we're going to try to find is we're going to try to get so close that essentially the distance between these 2 points is 0, and so that this is going to have a limit of 0. And so we're going to introduce some limit notation tomorrow. So if you want to kind of see what that looks like, you could type in either tangent line animation or secant line animation, and if you did that, then actually I don't know if this will, I don't know if it will work. I don't think it will, but I'll test it out. So what happens then is you can kind of see some pictures of a tangent line moving along the curve and seeing how its slope changes. Okay, so really what you're going to do today then is you're going to just estimate that. So by the way, another name for the slope of the tangent line is the derivative, and it's also called instantaneous rate of change. Those are all the same thing. So first of all, we can't do this for all functions. So we can't, it's called differentiable when you can find the derivative of something. So basically there are several times when you can't find the slope of the tangent line. So it has to be smooth or whatever, and it's got to be continuous. So the times when it's not differentiable, meaning you can't find the slope of the tangent line, would be a cusp. Okay, I'll show you what a cusp looks like two square root curves. A corner, a vertical tangent. Vertical tangent means, I'll give give you an example of the cubed root graph. Looks like this. It's got a vertical tangent right here. And also if it's not continuous. Okay. So as you're looking today, I might ask you some questions about that. Okay, so pretty much today you're going to just be estimating some slopes, and the way that I would like you to do that is you're going to, on your homework, you're going to use rise over run when I ask you to do these things. So use rise over run of these grids to do that. Let me give you an example. First of all, the first example is a line, negative 5x. Well, just bear with me here. Negative 5x. As I go along here, the points, because it is a line, the points are going to have tangent lines that all have a slope of negative 5. So if you're given a line, don't even bother trying to do rise over run. It's just the slope of that line. But let me give you an example, like x squared, for instance. If we put that in our calculator, and I'm going to do some things on here. I'm going to format, and I'm going to turn the grid on a minute. And I am going to go from negative 5 to 5. And let's see. Okay. So looking at that, I could try to, draw on the screen a little bit if I wanted to, and find the slopes of these lines. So remember, these are all tick marks. So if I wanted to try to draw a line, for instance, at 1, 1, okay? At 1, 1, if I was looking in here, I'm going to try to draw a tangent line, okay, with my pen. Could I find the slope of that line, okay? And so you could, if you tried to figure out what the tangent line was, like something along here, and tried to calculate the slope, maybe I would look and I'd say, okay, this thing goes up to here, that's up 1, 2 over 1. The slope looks like it's about 2, okay? So I'm going to say that at x equals 1, the slope is approximately 2. Right? So that's an example of what you're doing. Tomorrow we'll start investigating the definition, but today really I want you to just be able to approximate using rise over run on some graphs, the slopes, and then also talk, I ask you some questions about if you can find a derivative or not, yes or no, and why not.